This is an example of a problem similar to the problems on the 5 steps to a 5 extra drills questions that relate to Atwood machines. This is one that has friction. And so it's giving us the mass, this variable m equals 1 kilogram, and the coefficient of it would be kinetic friction is 0.2, and it's asking for the acceleration of the system and then the tension in each rope. In this case, we have 2 ropes to worry about. So let's number these. This is going to be, let's say, tension 1, and then this is going to be tension 2. Okay, so when we look at these problems, then it's not just a simple Atwood machine anymore, and we can't just use our tricks because we do have friction now. So we are going to write 2 equations and for 2 unknowns, which and then tackle our second rope at the end. So that's the way I go about it anyway. I'm sure there's lots of different ways, but the one thing I'm going to do to simplify this right off the bat is to combine these 2 blocks into one to like take these now and make them as if they were a single block, okay? And then treat them together and make that rope internal to the system and come back and figure that tension out later. And right now, just focus on tension 1 and acceleration. So also, I could just label these. This is really just 2 kilograms, and this is 3 kilograms. Okay, because I know what M is. So when I'm imagining the free body diagrams of these objects, I know that for this 2-block system, I would have tension, T1, I'd have normal, weight, and now this additional force of kinetic friction. And then for the hanging block, I have its weight, which should be longer, sorry. It's more massive than the 2 kilograms, so I'm trying to draw these to scale. And then it has tension, which is the same length as, it's got the same T1. Okay, so when I write the equations for each system, for the 2 blocks on the table, as you know, the 2 of them together, then I have, and I'm doing the X direction because the normal and the weight are going to cancel. So then these are going to accelerate, and so I would do mass times acceleration. So mass times acceleration is equal to, now I'm going to say here, girls, that this direction is positive for sideways motion, and I am going to be a rebel and say that down is positive for the vertical direction. And I got to be consistent because I need to make this make the rope move consistently, like always have the rope be moving in the positive direction as it goes over the pulley and not switch directions midway through. So if I follow that rule, then I am going to make T1 a positive force and then subtract force of friction. Okay, so then I know the mass is 2 kilograms. I am looking for A. I do not know T1 either. And then The force of friction is going to be the weight. It's really normal force, but normal force is the same size as the weight. And I know the weight, it would be 2 kg times 9.8 times the coefficient of friction. I'm running out of room. The coefficient is 0.2. Okay. So then if I'm gonna write this a little bit more neatly without the units, I guess, 2A is T1 minus it looks like, I think that this worksheet kind of rounds the gravity, so they rounded it to 4. They're keeping like whole numbers here. Okay. So then, if I'm going to also write an equation for the hanging block, so the F net for the hanging, okay, so then again, I would have mass times acceleration. Now the positive direction I said was down, so I'm saying Fg is a positive force, and I'm adding T1 as a negative. So then the mass is 3 times A, and then I've got 3 times 9.8, and then I've got my negative tension. So if I'm sticking with these like rounded off numbers, I believe that they're using like 30 here on their worksheet, 30 minus T1. Okay, so I have 2 equations and 2 unknowns. And in order to solve these simultaneously, I'm going to add the 2 equations. So that will help me eliminate, oops, T1. Because T1 appears like with no coefficients, and one of them is, this is positive, this is negative. So that's handy. So I've got 2A, and then technically this is like just negative T1 plus 30. So then this would be like around 5.2 meters per second squared. And then that came out positive. That means that the system is accelerating in this direction. Then I can go plug that back in to either one of these equations to find what is T1. So like if I plug it back in for in here, then I would have 10.4 So I have 10.4, which means that I get 14.4 newtons is T1. Okay, which should lose to gravity here. So this is 30 newtons of worth of gravity, and that doesn't surprise me that this is less Okay. And then one more thing, I'm supposed to find T2 as well. Well, the best way to find that, I mean, I could draw a free body diagram of just this block alone, or I could find just this block alone. So T2 is really either way. Let's draw a free body diagram of the last block. Like this block has 3 forces on it. It has T1, T2, and friction. Whereas this block has only 2 forces on it, T2 and friction. And I like, 2 forces better than drawing 3 forces. Okay, so then if I'm drawing that block, I have this last one. It's got T2, and then it's got FK in the X, direction that I care about. Of course, it's got these as well. But F net X is equal to T2 plus negative FK. And this would be mass times acceleration just for that block alone. I'm trying to find T2, and then the force of friction would be mu times normal force, which is going to be mass times g. Okay, so then this is 1 kg. I know the acceleration. That's the same for every single block. And then I've got 0.2 times 1 times 9.8. So when I do all the plug and chug here, now again, this worksheet tends to just round. So this would probably just be -2. And so they would have added that to both sides probably and called this 7.2 maybe. It should be less than T1 because this is responsible for pulling less mass across the table.